Okay, so let's take a look at section 8.1, the notes for this. This is the first part of chapter 8. And so the first part is actually on something that we studied last semester called direct variation. So this thing right here. Whoop. This thing. Direct variation. Here's the definition for it down here. So remember, direct variation, y and x vary directly if y equals ax. And then a is some constant that's not 0. And so the idea is like if y gets bigger, x gets bigger too, or if y gets smaller, x also gets smaller. And so whatever y does, x does in the same direction. That's generally the idea. So let's kind of review it a little bit. Give a couple examples of equations that show direct variation. Well, let's see. We really just need something in this form, y equals ax. So y equals 3x would be one example, right, where a is 3. So that's one example. I'll show you how they kind of end up disguised a little bit. If you did this one, y equals x over 4. Sometimes you see something like that. Really, if you do a little rearranging, that's the same thing as saying y equals 1/4 times x. So the a is the 1/4 there. So that's an example of direct variation. Here's one that, to me, doesn't originally look like direct variation at all. X over y equals 2. But if you rearrange a little bit and you solve for y, because we want y by itself, then you're going to get, first multiply both sides by y, so you get x equals 2y. And then divide both sides by 2, and you get 1/2 x equals y. So your a is 1/2. This is in the form y equals ax now. Y equals half x. So this one, a would be a half. So those are some of the forms that you can end up with. So all three of these guys are actually showing direct variation. It's just that you have to manipulate them so that they look like this form, y equals a to the x, y equals a times x to get that. In 2, we're told x and y vary directly. So as soon as you see this line, you know you're going to use the equation, the general form y equals ax. Right? And then you know y is 12 when x is 2. So for part A, when you have to find the equation that relates x and y, you're just going to plug in into y equals ax. So 12 equals a times 2. So then you get a is 6. And then that's not the equation that relates x and y. The equation is when you plug it back into here. So it's y equals 6x. That's the answer to part A. Then for B, we can use that equation. We know y equals 6x now. And it says find y when x is 7. So when x is 7, y is going to be 6 times 7, which is 42. So that's our answer to B. All right, let's keep going. Okay, so that's the review of direct variation. We'll come back in a little bit to it. Inverse variation is this one. Y equals a over x, not a times x. Right, so the idea is if y gets bigger, x has to get smaller and vice versa. So they whatever one does, the other does kind of the opposite. A is still called the constant of variation like it is in direct variation. So you just have to realize the a is on the x is on the bottom for inverse variation, the x is on top for for direct variation. So a couple of examples that show inverse variation. Simple one would be like y equals 3 over x, and then that one a is just 3. But then they kind of show up disguised sometimes again, like y equals 1 over 2x. Well, really you can think of that as 1 over 2 times 1 over x. This form right here is the same thing as y equals a times 1 over x. So if you can get the constant in front, that's really the same a that would normally be on top here. Because you could also write this as 1 over 2 over x, but nobody really writes it this way. So in this one, the constant of variation right there is the 1/2. And then another type that can show up is if you have something like xy equals 7, let's say. So if you want to solve for y there, you've got y equals 7 over x, right? So that means that the 7 is going to be your constant of variation. So 7 equals a in this one. Let's do one more. So you could also sometimes see it as x over y equals, oh no, sorry, never mind. That's it. Thinking of a different example. All right. So in number 4, suppose x and y vary inversely. So as soon as you see this line, you should know that you're going to use the definition of inverse variation, which is y equals a over x. Or you could use this form if you prefer that. So let's write y equals a over x, because it's inverse, not direct. Okay, so y equals a over x, and y is 7 when x is 4. So y is 7 when x is 4. And then if I multiply both sides by 4, I can get a. So a ends up being 28. And so that's not the equation that relates x and y. The equation that relates x and y is going to be y equals 28 over x. I'm just plugging it back into here. Actually, let me take away that box, because that's not really the answer here. This one's the answer. Okay, and then in B, find y when x is negative 2. Well, I now know y is 28 over x. That's the inverse relationship. And when I plug in negative 2 for x, we get negative 14 for y. So there we go. That's B. Okay, so let's keep going. And this one, the question is, are you looking at direct variation, inverse variation, or neither? Okay. All right. So 3x equals y. Well, that's in y equals ax 4, right, where a is 3. So this one right here is direct variation. So this one, direct variation. In B, we've got xy equals 0.75. Well, you're supposed to solve for y to figure this out. So y equals 0.75. You'd have to divide both sides by x. Well, now that's in a over x form, right? Y equals a over x form. So I'll do this. I'll put these in parentheses. Y equals a over x. That means that it's going to be inverse variation. By the way, inverse here, it's not the same thing that you're thinking of where you switch the x's and y's. That's different. So this one, you have to think of it as a different, inverse in this case kind of means like flip the fraction. So, okay. In C, we've got y minus 3x equals 0. Well, we'll solve for y, and we get y equals 3x. That's actually the same thing as part A. It's in y equals ax form. So that's going to be direct variation. Okay, in D, we want to solve for y. So if we do that, we get y, we'll multiply both sides by y. So we get y times x equals just 3. And then to get y by itself, I'm going to divide both sides by x. So I get y equals 3 over x. Well, that's y equals a over x form. So this one's going to be inverse variation. In this one, if I solve for y, I get y equals 5 minus x. Well, that's not y equals a times x form, because there's that plus 5 there. And it's also not y equals, whoops, y equals a over x form, because there's no x in the denominator. So this one is neither direct nor inverse. And then the same deal down here in F. It's not y equals a x form, not y equals a over x form because of the minus 5. So therefore it's neither. Okay. In 6, we're trying to figure out, does this data fit direct variation, inverse variation, or neither of them? Okay, so let's just check direct first. So first, check direct. So the idea there is then the y's would have to fit some equation, y equals ax. So let's figure out what the a would be. Right? So if we pick the first data point, 40 equals a times 1.5, and we'll solve for a. So if I divide both sides by 1.5, divide by 1.5, whoop, oh, I don't know what happened there. 1.5. Then let's see, what do we get? We get a equals 26.6 repeating. So then this means that the data has to fit y equals 26.6 repeating x. Well, what we can do then is plug in the other points, all the other points, and see if that works. So let's try this. Let's try, so this is when we figured out what a would be if that works for direct variation. So then let's check if this one works in the equation that we got. So if we plug in 24, we get 26.6 repeating times 2.5. So I'm plugging in the x and the y. And it turns out, no, this is much bigger than 24. So no, this doesn't work, right? So not direct variation. If you wanted another way of approaching it, you can basically solve for what a would be here, solve for what a would be there, solve for what a would be here, solve for what a would be there. And if they're not all the same a, if any one a is different, then it's not direct variation. The a has to be the same in every case. So that's another way of approaching it if you wanted to. Okay, so let's do inverse. Okay, and in this one we're checking y equals a over x. So if we try the first point right here, so 40 equals a over 1.5, then we'll figure out a has to be 60. So then we've got the equation y has to be 60 over x for every single data point. So we're going to check, do those points work and y equals 60 over x? Well, we know it's got to work for the first one because I just checked it. So now we'll try the next point. So y equals 60 over x is what we're checking. And if I plug in 24 for y, I'm checking this point now. Then I want to see, is that the same as 60 over 24? Or sorry, 60 over 2.5. And it turns out it is, so that point's good. So then let's try it with 4 and 15. So y equals 60 over x is our equation. And we're checking, does that work when y is 15 and x is 4? And yeah, that one works too, so that's good. And then if I try it with my last set of data, I plug in 8 for y. Oh, let me write the equation first. Y equals 60 over x is what we're testing. And if I plug in 8 for y and 7.5 for x, is that equal? And if you plug that into your calculator, yeah, it's equal. So, and then of course the original data point has to work because that's how we got this equation in the first place. But if you really wanted to check it, say, okay, if I plug in 40, is that the same as 60 over 1.5? Which it is. So all the data fit y equals 60 over x. So the data show inverse variation. That's one way of doing it. Another way that you could do it, if you prefer this, is set up each one of these with a y equals a over x, where you don't have the a, and solve for a with this set of data, this set of data, this set of data, this set of data, and in each case you're going to get a equals 60. And since they're all 60, since all of the a's would be 60, then you can say, okay, it's inverse variation. If you end up with any sort of different a for one of them, then it doesn't work. Okay, so let's check joint variation. So joint variation is really just direct variation, but done repeatedly. So if I say z varies jointly with x and y, then z varies jointly with varies directly with x times y. You can kind of think of it. If I say p varies jointly with qrs, then you just have a times qrs. Okay. So then if we look at 7, it says C varies jointly with T and U. So as soon as you see that, you've got C equals something times T times U. That's your equation. And then they tell you, well, C is 60 when T is -4 and U is 5. So 7A here. If I plug in 60 equals A times -4 times 5, well, I can divide both sides by -20. This cancels with that, and I get -3 equals A. So now I know C has to be -3 times T times U. And that's going to be my equation that relates C, T, and U. And B, I'm trying to find C when I know T and when I know U. So C equals -3TU, and then I'm just going to plug in for the T and the U. -3 times 7 times 2. Well, that's going to be -42 for C. All right. Okay, let's move on to 8. So write an equation for each relationship below. So the first one's pretty basic. Y varies inversely with X. Well, that means that Y has to be A over X. That's inverse relationship. Okay. Z varies jointly with X, Y, and R. Well, that means that Z varies directly with X times Y times R. Just like that. Okay, the last one's a little bit weirder because it does a joint one and an inverse one, right? So the way that you do that, whoops, sorry about that. The way that you do this, right, is, well, P varies jointly with R and T. Well, that would be A times R times T, but inversely with the X squared, the square of X, that's X squared. So that means that you have to throw the X squared underneath because that's inverse. If I just said P varies inversely with X squared, then that would be P equals A over X squared. But if I say and directly with like root W, then you have to throw a root W on top. So directly or jointly goes on top, inversely goes on the bottom, and you always have to have an A. All right. So let's take a look at 9, and then that's the last problem here. So write a model that gives, or no, first we've got number of songs that be stored on an MP3 player varies inversely with the average size of a song. Okay, so number of songs, which is N, number of songs, and S here is average song size. And we were just told that the number of songs varies inversely with average size. So N varies inversely with S. And so that means N equals, since it's inverse, S goes on the bottom. N equals A over S. Okay, and then we know when you have 2,500 songs, the average size is 4 megabytes. So 2,500 is N equals A over 4 megabytes. And then if I multiply both sides by 4, I get 10,000 equals A. So then the model is going to be N equals 10,000 over S. So there's my model. Okay, N varies inversely with S, and the constant of variation is 10,000. So then use your model to figure out how many songs will fit on the MP3 player. If the average song size was 5 megabytes, well, that's S equals 5. Find N. So we just do N equals 10,000 over 5, which is 2,000. So you can fit 2,000 songs on your MP3 play on that MP3 player if the average size was 5 megabytes. Okay, hope that helps a little bit.